turned out to be so nice once we get all this done. So easy. No quotient rule or product rule needed. So the last step before we do the derivative here, powers come out. So we have 2 ln of x plus 4 ln of x minus 3 minus 6 ln of x plus 5. So we do all that work, and now we're ready for our derivative part. So after we get it all situated, expanded, I guess you might call it, these logarithms, of course the expansion here was much easier, but turns out the derivative here is much easier because, all right, so now we ddx both sides, do the derivative. You got the same thing over here, 1 over y times dy over dx, y prime. But what about the derivatives here? What's the derivative of 2 ln of x?
2 over x.
2 over x? Yeah, ln of x, the derivative is just 1 over x. What's the derivative here? Well, you might say, well, I got the chain rule here, but it's just x minus 3, so it's 4 over x minus 3, right? And then the derivative of the inside is 1. It's just 1. So, yeah, these work out as well. And then minus 6 over x plus 5 is the derivative of the inside is 1. Yes? So solve for dy over dx. So dy over dx is going to be y times that. So multiply both sides by y. Let's do it this way. But y is that, so I mean that's the hard part, I guess. This long part. Times just all of this. 2 over x. It's 4 over x minus 3. Minus 6 over x plus 1. So, all right. It's called logarithmic differentiation. Is that okay? Question? Sir? All good? Okay, let's talk about another piece here of our puzzle for differentiating and integrating. This too is probably more for integration purposes. We have to talk about the derivative though first. But the inverse trig functions. The inverse trig functions are going to give us some more integrals that we can handle out of them. The inverse trig functions. So just start with here, just kind of a brief little review of what we mean by the inverse trig functions. The inverse trig functions are not 1 over cosine, 1 over, that's not what we're talking about. We're talking about the inverse of them. And the way we write them, remember, it is, well, sine inverse. The inverse sine is written this way. That's not the same as, we had this earlier, one of them. It's not the -1 power. That's not what, a lot of times you can move that power and say that's you can't do that for this notation. It's the inverse sine. It's the y equals sine inverse of x. That's the y here is the value such that the sine of y equals x. So that's where it comes in the, why we call it the inverse sine. So this, what we're looking for here, the y here, the y is the y is such that the sine of y equals x. And then you have to specify here the x here that you get, the y value has to be between, the y value here is between -pi/2 and pi/2. So maybe an example here, just to kind of refresh your memory maybe. Well, some of you, if you haven't gotten there yet, but here's what it means. You won't have to, you may have to do a few of these, so here's what it is. So say I want sine inverse of 1/2. Well, we're looking for, well, what? Let's just call it y here, since that's kind of what we got labeled there. So the way this works is I'm looking for, I'm looking for the y such that the sine of y equals 1/2. So you can think of the y here as an angle. What angle gives me that sine value? The sine of that angle is 1/2. Well, you think about sine of 0 is 0, so it'd be sine of 30 degrees, or pi over 6 would give you 1/2. Right? So the y here is pi over 6. So the sine inverse of 1/2 is pi over 6. So that's what we're saying. It's kind of the inverse of operation of what we usually do with sine. Sine inverse of 1/2 is pi over 6. Now, this comes into play because, this number, because there's other values whose sine is 1/2, like, what other one would be? 5 pi over 6. Sine of 5 pi over 6 is 1/2, but that wouldn't fit into the range here. Y has to be between negative pi over 2 and pi over 2. So anyway, that's just like I said, it's not trying to teach you that, it's just showing you what that is, reminding you or whatever, okay. So we usually work with sine inverse, tangent inverse, cosine, the others have it as well. Tangent inverse, sort of a similar deal. The y is also between negative pi over 2 and pi over 2. The cosine inverse is a little different. It's between 0 and pi. The y comes out there between 0 and pi. I don't know how much, I mean, if you put it in the calculator, it'll well give you the decimal equivalent of that. It'll take care of that, but just to remind you. Okay. Well, so our goal is not to learn that or go through all the ins and outs of that. Our goal is to figure out what about the derivative of that, right? And it's really more about what it would mean then for the antiderivative situation. So these are important. Okay. All right, so we've got y, let's do something. All right, well, not knowing what it is right off the bat, let's try to go with something we do know, and then maybe we can go from there from then on. We won't have to do this every time, but all right, so like we just said, that converts over. If I convert that over to something just with the sign, remember what we said, y equals sine inverse of x means the sine of y equals x, right? That's also, you might say, an alternative form of that, right? Well, okay. Can I do some implicit differentiation there? If I'm trying to find y prime, I can do these. I know the derivative of that. I know the derivative of that. Yeah, so let's do dx both sides here. What do we got there? Cosine y, but it's the derivative with respect to x, so I need dy over dx. And then this side is just 1, so dy, oh, look at that. Dy over dx is 1 over cosine y. The problem is, we started out with sine inverse of x. So that doesn't tell me a whole lot about what this is. There's a much better much better form of this. And it's using the, kind of using the trig, some trig identities. You know, cosine squared theta plus sine squared theta equals 1. Yeah, we'll drag out trig identities from time to time here. So let's solve this for cosine. 1 minus sine squared, I guess we could have started with that. That's probably pretty well known, but now it'd be plus or minus, I guess, there. But since I'm cosine, so in yeah, the cosine here, it amounts to we need the positive side of this for the for this particular case, we worked our way back through it. You need the positive counterpart to that. So let's rewrite. So 1 over cosine y using that, and it's the positive, not the negative, because of the restrictions on x and all that, or restrictions on y. Anyway, it's 1 minus sine squared y squared root. We're almost there. That's still in y, but what's sine of y? It's x. So it turns out dy over dx is 1 over the square root of 1 minus x squared. Dy over dx is 1 over the square root of 1 minus x squared. All right, so we'll just use that. So the ddx of sine inverse of x is 1 over the square root of 1 minus x squared, which is kind of nice, or notice there, that's not involving a trig function at all. We started with an inverse trig function, for sure, but the derivative is not a trig function, right? There is a restriction on x here because you're talking about you have to have a positive square root, so x would have to be between 1 and negative 1. Well, that's what x starts here as. X is between 1 and negative 1. Can't do the sine inverse of anything besides those, so it all works out. All right, we won't go through it, but similarly, we can do the cosine inverse of x. It turns out it's negative of that, 1 over the square root of 1 minus x squared. Tangent inverse it's pretty nice too. Matter of fact, it's nicer. It's usually written 1 over 1 plus x squared. So the derivative of the tangent inverse is 1 over 1 plus x squared. And then I have the others on that formula sheet, but those those are the ones really, well actually, this one and this one are really the main ones that we need for antiderivative purposes, but the others, cotangent inverse is negative of that. The cosecant and secant inverse, those are also similar. They're related by positive and negative of each other. Okay. Okay, so if I have, so if y equals sine inverse of x squared, of course, yeah, what they'll do is they'll just throw the chain rule in on it. What does that mean here for the derivative? Well, there's our derivative of the sine inverse. So what would this derivative be? Well, it's chain rule, outside, inside. So the outside is the sine inverse, so it's that. However, what's my x here?
X squared.
Yeah, so it's x squared. So you got to square x squared here. So instead of x, I've got x squared, so you got to square that. So it'll be x to the 4th. And then we've also got to factor in the derivative of the inside, which is 2x. So it's just, stuff like that you got to look for. Whoops, I guess we do it that way. Okay. All right. But like I said, what this really opens up is what these are more useful for is, because you probably don't see a lot of the sine inverse in applications, but what this does open up is some more antiderivatives, some more integrals. For example, if I have just the integral of 1 over 1 plus x squared dx, or dx over 1 plus x squared, what do you got? What? So this, I want the antiderivative of this. So I'm looking for this, where this, the derivative of this is that. Do I have anything whose derivative is that? Tan inverse, yeah. The derivative of tan inverse is that, so the antiderivative of 1 over 1 plus x squared is tangent inverse. Let's see. And then also the other one is this one. What was that one going to be?
Inverse sine.
Inverse sine. Yeah. Sine inverse, the derivative is that, so the antiderivative of that would be the sine inverse. And those are also a couple other ones I have on that formula sheet. Notice that. Okay, well, of course, the other thing is, well, how do I use those and kind of expand on those? Well, glad I asked you, right? Okay, so let's do, all right, the integral square root of 1 minus 4x squared dx. Well, we always say try u substitution first. The problem with u substitution is if I let u be that, what's going to be the problem? My dx would be, I guess I could write it out, just to kind of hash through some things here. So my du would be minus 8x. What's the problem with that? I don't have any x to counteract that, do I? So that is not going to be that anyway. That extent of u. However, this is a u. Yeah, it is a u substitution here. It's just I can't do it that way. No, what this, the next thing then, well, that kind of reminds me of this. It's just that it's 4x squared instead of just x squared. It's square root of 1 minus 4x squared. So what do I need? Well, it is a u substitution here, but not that u substitution. All right, so for this to work, I would need it to be 1 minus something squared, 1 minus u squared. How would I make this 1 minus u squared here? U is what? 2x And that would make it then the square root of 1 over the square root of 1 minus, whoops, so du, I better put my du too. So du over 2. So that would make this then, it's 4x squared, so if u is 2x, that's u squared it. And then du over 2. Now I'm good. What is my antiderivative? Well, you got the 1/2. This turns into sine inverse. So it'd be sine inverse of u. 1/2 times sine inverse of u plus c. So that's 1/2 sine inverse of 2x plus c. Okay, one more, then I'll be done. This one has another little twist to it, I guess you might say. So again, our u substitution, we might, well, let's just substitute denominator to be u. U equals 6 plus 36x squared. But we run into the same problem here because our du in that case would have something over x. Du over something in x. And there's not an x to cancel that out. And so that means you can't do that u substitution. However, yeah, that one's, since I've got it right here, that one's more set up like a tangent inverse, isn't it? Well, the problem with this one is, the extra problem with this one is, yeah, this one has a 6 instead of a 1. So yeah, you do have to make that 1 factor out of 6, first of all. And then think of it as 1/6 times. Yeah, so that 1/6, you can factor it off, bring it out. Okay. So now we can do similar to what we did with our previous problem here. I need this though to be something, just something squared. 1 plus u squared. So if I want that to be u squared, what does u need to be? A little trickier, isn't it? So 6x squared needs to equal u squared. Think of it that way. So square root everything. Oops. That kind of tells you what u needs to be. Wouldn't it be the square root of 6 times x? Yeah. So we need this to be u squared. So you need to say 6x squared needs to be u squared. So that makes u just square root both things. Square root of 6x. So that would make du square root of 6 times dx. So d over the square root of 6 is going to be my dx. 1/6 times, that would make it 1 plus 1 over u squared, and then du over square root of 6. So I got it, don't I? That's now, well, I've got the lovely little 1 over 6 square root of 6 there, or 6 to, maybe 6 to the 3 power, but what about this? Well, that's just now a nice antiderivative, isn't it? Yeah. It's tangent inverse of u. See? And then just change that back to x. What was at square root of 6? I mean, what was u? Square root of 6x. Okay. Yeah, those. So it opens up. I couldn't have been able, if I didn't have these, I wouldn't have been able to do these by u substitution. But